everybody, my name is Zach, and today we're learning about rotational molding. So this is our rotational molding machine. So as it implies, we're going to be taking some powdered plastic, filling it inside this mold, then we're going to seal it, heat it up till it's a complete liquid, and then rotate this on both axes to completely coat the inside of the mold. This will give us a solid object with 0 holes in it, and that's a unique feature about rotationally molding your parts.
So now before we dive into this process, we need to calculate how much plastic we're actually going to be adding to the mold. So today we're going to be making a basketball. It's a hollow sphere. We know what its final diameter is going to be because we know the diameter of the inside of our mold. And we also know what we want the final wall thickness to be. And using these, we can calculate the mass of the plastic that we're going to use. Now I won't be doing the calculations for you in this video, but I will show you an easy way to set up this problem. Now rather than thinking about this problem as a single hollow sphere, I think it's a lot easier to think of it as 2 spheres. We have one sphere of plastic, and then inside of that we have a sphere of air. Now we can use the old reliable equation for the volume of a sphere and find the volume of the outer sphere and the inner sphere and subtract them to get the total volume of the plastic in this part. Then all we need to do is multiply that by the density, and we have the mass of plastic that we need to make this basketball. With that figured out, we can measure out the amount of plastic that we calculated and carry on with the process.
So a lot of times when we're trying to get our parts out of the mold, just because of the nature of this process, it's really hard. The plastic tends to bond or try to bond it inside our mold. Luckily we got this mold release here. It's a special chemical that'll kind of lubricate the inside and allow us to get it out nice and easy.
Next, we can go ahead and fill the mold and seal it up.
So now let's check the parameters that we have our oven running at. So we've set the thermostat to 325 degrees, but we only got an actual temperature of just below 325. We'd expect some losses there. Next, the speed that we're going to be rotating at, we have that set to 55% of the motor's full value. And last thing we should check is the oven's pressure. One atmosphere. This oven isn't pressurized.
Now we're going to insert our mold into the oven and begin the process. We're going to leave it in there for a whole 25 minutes to ensure it's fully liquefied and fully coats the inside of the mold before we remove it. You'll notice that as soon as the motor turns on, the mold begins to rotate on 2 different axes at the same time. This is crucial to fully coating the inside of the mold without leaving any thin spots or thick spots. Next, we take the mold out of the oven and quickly cool it down. This is to harden the plastic in its uniformly coated state and not allow the liquid to flow to other parts of the mold, messing up our final product. Once the part is fully cooled down, we can crack open that mold and see what we got.
Nice.
Next, we cut off the flash from our part and take it to the scale. Here we see our final product weighs 163.9 grams. If we subtract that from the initial plastic we put in weighing at 164.5 grams, this process only produced 0.6 grams of scrap. In the end, even though rotationally molding is a pretty slow process, it's been able to cement itself in industry by making parts that other manufacturing processes just can't make. On top of this, rotationally molded parts and products tend to be really high quality and very durable. That's all I have for you guys today. Thank you for watching, and I'll catch you in the next lab.